Welcome to the lecture on synthetic division. Synthetic division is a shortcut that we use instead of long division, but it can only be used in very special cases. You can only use synthetic division if you are dividing by a linear binomial. That means you need to be dividing by something with x to the first power in it. For example, in this example, we've got 4x cubed minus 3x squared plus 2x minus 3, but what we're dividing by is x minus 2, and that's an x to the first power, so it's a linear binomial. And binomial, remember, means two terms. So what you have to be dividing by is something of one of these four variations, either dividing by x plus a number, x minus a number, ax plus a number, or ax minus a number. Here's how synthetic division works. The reason it's a shortcut to long division is it enables you to ignore the variables and just keep track of the coefficients and the actual calculations that you need to use. So what we're going to do in this first example is take the coefficients only of the original polynomial. So here I have 4, then I have a coefficient of -3, coefficient of 2, and a coefficient of -3. Now, just as with long division, you want to make sure that every single term has been accounted for. We've got our x cubed term, x squared term, x to the first term, and constant term. If any of these terms had been missing, you would want to use a 0 in its place for the coefficient that you list up above. In a little box off to the side in synthetic division, what we are going to put is the number that we're dividing by. And the way that you figure that out is by looking at the linear binomial you're dividing by, this part right here, and you find where that linear binomial would equal to 0. And in this case, where does x minus 2 equal to 0? At +2. So we're going to divide by a 2 in that little box. If you look at the sign of our 2, it's exactly the opposite sign of what we see in these parentheses. So here's how the algorithm or the process goes for synthetic division. It's actually quite simple once you get the hang of it. You're going to draw a line and leave some empty space in between here. In the very first step of synthetic division, we take this first coefficient and you bring it down unchanged. Then you're going to take any number below this line and multiply it by 2. And you're going to write that answer in the middle spaces up here. So for example, we're going to take 2 times 4, and that's 8. Now to get the number below the line, you're going to add down. So -3 plus 8 is 5. Then we multiply again. 2 times 5 is 10, and then you add down. 10 plus 2 is 12. Then we multiply. 2 times 12 is 24. And then we add down. -3 plus 24 would be 21. So when we get our final solution, we're going to say that this number in the end is our remainder. And these numbers left to the left of that remainder are the coefficients of our quotient. So to write out your final solution, you have to remember that these coefficients that we started with were x cubed, x squared, x, and a constant term. So this was a cubic polynomial to begin with. If we divide a cubic by an x to the first power, then the answer is going to go down by 1 degree. So in other words, if this was a cubic to begin with, our quotient is going to be down to an x squared. So the coefficients that you see down below this line should always be 1 degree less than the degree you started with. So if we start with degree 3, then this first coefficient is going to be of a degree 2 term. And then the 5 here is going to be 1 degree less than that, which is 5x, and the 12 will be our constant. So here's how we write out our final solution. It would be 4x squared plus 5x plus 12. That's our quotient. But we had a remainder in this example, so we're going to write out our remainder with a little remainder fraction. The number that we ended up with right here is the numerator of that remainder fraction, and the denominator is the linear binomial that we were dividing by originally. So this would be 21 over x minus 2. So we have our quadratic quotient right here plus our remainder. Okay, so let's try this again. It seems a little tricky at first, but again, it will become very simple once you get the hang of it. First thing we do is we take our numerator in this case, and we take those coefficients and we list them in descending order across. So we're going to go 5, that's our first coefficient, then -6, then 3, and then 14. In the little box off to the side, you're going to be putting the number that you want to divide by, and that should be wherever this linear polynomial equals to 0. And where does p plus 1 equal to 0? When p is -1. Remember, it's just the opposite sign. So if this is a +1, we're going to see a little -1 in that box. So you list your coefficients across the top, you list the number you're dividing by in the little box, and then you draw your line. Here's how the algorithm goes. You bring down that first coefficient unchanged. Then we're always going to be multiplying the number below the line times -1 and writing that across the middle. So -1 times 5 is -5. You add down -6 plus -5 is -11. And we multiply again. -1 times -11 becomes +11. And then we add down again. 11 plus 3 is 13. Excuse me, 14. Sorry about that. Then we're going to multiply again. -1 times 14 is -14. And then we're going to add down. 14 plus -14 is 0. So we multiply the numbers below the line, and then we add down to get the number below the line. The number in the farthest right corner is your remainder. In this case, we got a 0, so that means we have no remainder. What these coefficients represent right here are the coefficients of your quotient. And to figure out how to write that correctly, remember that the first coefficient right here should be the coefficient of the term 1 degree less than what you started with. We started with a p cubed, so this is 1 degree less, or p squared. And then the next coefficient will be 1 degree less than that, and then the last coefficient here is going to be a constant. So your quotient, or your answer, is 5p squared minus 11p plus 14, and since we had no remainder, we don't need any remainder fraction. Okay, let's try another example. Now the next one here, notice on the top, starts with an x to the 4th, and then it jumps all the way down to that constant. So the x cubed term, the x squared term, and the x term are all missing in this numerator. We want to make sure that we account for those because we may need them when we divide. So when I list out my coefficients, this is a coefficient of 1 in front of that x to the 4th. There's no x cubed, but I'm going to hold its place with the 0. There's no x squared, but I'm going to hold its place with the 0. There's no x term, but I'm going to hold its space with the 0. And then finally, we would get down to that constant term, which was 81. What we're dividing by is where this denominator would equal 0, and that's going to be at +3. So that 3 goes in our little box off to the left. And we're going to draw our line. The first coefficient comes down unchanged, and then we multiply. 3 times 1 is 3. Add down. 0 plus 3 stays 3. Multiply again. 3 times 3 is 9. Add down. 0 plus 9 stays 9. Multiply again. 3 times 9 is 27. Add down. 0 plus 27 stays 27. Multiply one last time. 3 times 27 is 81. Add down. Unfortunately, these are both positive, so they don't cancel out, so we get 162. The number in the furthest right corner is your remainder, and these coefficients that you have right here are the coefficients of your solution 1 degree less than what you started with. We started with an x to the fourth, so this is going to be 1 degree less, or x cubed. The next coefficient is for x squared, the next coefficient is for x, and the last coefficient is your constant. So our answer is going to be x cubed plus 3x squared plus 9x plus 27. And then we did have a remainder, so we're going to write that as a remainder fraction. We add our fraction, the 162 goes in the top, and what we were dividing by originally, which in this case was x minus 3, goes in the denominator. So here's our final solution. So it's really quite quick and easy as long as you are dividing by a linear polynomial. Remember that synthetic division only applies if you're dividing by an x to the first power. If this was an x squared or x cubed or anything higher in that denominator, then the only way to divide would be by using long division, which works, but it's pretty tedious, so we try to avoid it if we can. Okay, our last example. Here we have a cubic divided by, again, a linear polynomial. This is x to the first power. That's what tells us that we can use synthetic division. So I'm going to take these coefficients and list them going across. 2, 5, negative 11, 4. All terms were accounted for. I had an x cubed, an x squared, an x, and a constant. So I don't need any zeros. What's going to go in the little box? This time it's a little bit trickier. What we're dividing by here is 2x minus 1. So to figure out what goes in that box, you need to find where that linear binomial would be 0. And if we solve this by adding 1 and then dividing by 2, the solution to where this would equal 0 is actually a fraction, 1/2. So we're going to take that fraction 1/2 and put it in our little box. It's a positive 1/2. So now we perform our algorithm. We draw our line. The first coefficient comes down unchanged. 1/2 times 2 is 1, and we add down. 5 plus 1 is 6. Then we multiply again. 1/2 of 6 is 3, and we add down. Negative 11 plus 3 is negative 8. Then we multiply again. 1/2 of negative 8 is negative 4, and when we add down, 4 minus 4 is 0. So that is our remainder. We have no remainder this time. And these are the coefficients of our solution, which will always be 1 degree less than what you started with. You started with an x cubed, so this is a 2x squared. This is a 6x, and that negative 8 is your constant term. So our solution is 2x squared plus 6x minus 8. Okay, just remember that synthetic division, a quick and easy alternative to long division, as long as you are dividing by an x to the first power only. If it's a degree higher than x to the first, you have to use long division. Okay, let's take a look at the polynomial function p of x equals x cubed minus 5x minus 2. The first question I have is, let's find p of 2 by substitution. So our input is 2, and that means all we're going to need to do is substitute in 2 for each of these x's. So p of 2 is going to become 2 cubed minus 5 times 2 minus 2. And if we simplify, 2 cubed is 8, 5 times 2 is 10, 8 minus 2 is negative 2, negative 2 minus 2 is negative 4. So p of 2 equals negative 4. Now let's try another question that might seem somewhat unrelated. Let's use synthetic division to find the remainder when p of x is divided by x minus 2. So since our polynomial is x cubed minus 5x minus 2, notice there's no x squared term, so we need to hold a spot for it by using a coefficient of 0. So my coefficients are going to be 1 for the x cubed term, 0 for the x squared term, negative 5 for the x, and negative 2 for the constant. And since we're dividing by x minus 2, that's going to equal 0 when x equals 2. So the little number I want to put in my box is just a 2. So here's my setup. Now we're going to go ahead and do our synthetic division. So the 1 comes down. 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. Negative 5 plus 4 is negative 1. Negative 1 times 2 is negative 2. Negative 2 plus negative 2 equals negative 4. Now here's the connection between these two problems. The remainder that we just got was negative 4. Notice that that is exactly the same thing we got when we substituted in 2. So it turns out that this is a very important theorem. It's called the remainder theorem. And what it says is that the remainder that you get when you divide a polynomial by x minus c is the same as substituting c into that polynomial. So the remainder will be the value of p of c. Now this can come in handy in a couple of different ways. So let's take a look at a couple of examples. The next example here, we've got this big 6th degree polynomial, and we want to find the value of p of 4. Now you could do that by substitution. If you didn't have a calculator, that would get pretty nasty because 4 to the 6th power and 4 to the 5th power and all of these coefficients, that's going to get to be pretty large. So instead of using substitution, let's try the connection that this value of p of 4 is exactly equal to whatever the remainder is going to be when I use synthetic division. So if we use synthetic division instead of substituting in, we can find the value of p of 4. So my coefficients for my polynomial are 4, negative 25, 35, there's no cubic term, so I'm going to use 0, 17 for the x squared, there's no x term and there's no constant term, but I still need to hold their place with zeros. Now, if I want to find p of 4, then up here, remember that's asking for p of 4. What must I have been dividing by? X minus 4. So the little number that we're going to put in our box is exactly the number that we would have substituted in. So I'm going to use 4 in this little box. So let's do our little substitution. If I bring down my 4, 4 times 4 is 16. Negative 25 plus a 16 is negative 9. Negative 9 times 4 is negative 36. 35 minus 36 is negative 1. Negative 1 times 4 is negative 4. Adding down gives me negative 4. Negative 4 times 4 is negative 16. 17 minus 16 is 1. 1 times 4 is 4. 0 plus 4 is 4. 4 times 4 is 16. And adding down I get 16. So my remainder is 16. And by the remainder theorem, that means the remainder that was 16 must also be the value that I would have gotten if I had substituted in 4 into the original polynomial. So the value of p of 4 must also be 16. They match. The remainder and the value from substituting are always equal. Let's try one last example here. So this time I want to do some division. I want to take this big 100th degree polynomial and divide it by x minus 1. Now if we were just going to go ahead and figure out how to divide this using synthetic division, this is a 100th degree polynomial. So my 100th power coefficient is 1. There's no 99 degree power, so I'd need a 0. My 98th degree term has a coefficient of negative 2. And then you can see how tedious this would be. We need a 0 for the 97th degree term, 96, 95, 94, all the way down until we got to that square term. There's no linear term, and then the constant term is negative 1. And then we'd want to put a little 1 in the box since we're dividing by x minus 1. Now that's a lot of zeros to keep track of, and you probably can see that this is not really something we want to do if there's so many coefficients since it's such a high power. So this is where that remainder theorem can really come in handy. Since all we want to know is what the remainder is, the remainder of dividing by x minus 1 is going to equal the value of 1 substituted in to the original polynomial. That's by this remainder theorem. So instead of doing all this long division with all these zeros that we're missing, we can take our polynomial, which is this 100th degree polynomial. I'll call it p of x. So p of x is x to the 100 minus 2x to the 98 plus 7x squared minus 1. And the remainder by dividing by x minus 1 is going to be the same as what I would have gotten if I had just substituted in 1 into this polynomial. And that's really easy to calculate. 1 to the 100th minus 2 times 1 to the 98th plus 7 times 1 squared minus 1. So that's 1 minus 2 plus 7 minus 1. So negative 1 plus 7 minus 1. So that's 6 minus 1, or 5. So instead of doing all that long division with all those zeros because it was a 100th degree polynomial, I can just substitute in 1 and get my remainder very, very quickly. So use that remainder theorem to help you simplify a problem. If it's too long to do synthetic division, then use substitution. If it's too tricky or too complicated or too tedious to do substitution, then try synthetic division. Alright, that concludes our lecture notes on synthetic division and the remainder theorem. Good luck.